Real exam questions. This is question 38. It's about slab design with yield lines. A balcony supported on 3 sides is loaded with a uniform distributed load Q. Optimize lambda so that the plastic bending moment is maximum under the condition that lambda is smaller than 1 and beta is bigger than 2. Determine lambda as a function of beta. For what value of beta is lambda equal to 1? So for what value of beta is this angle 45 degrees? Determine the maximum plastic bending moment for a balcony of 1.5 by 5 meters loaded with 10 kilonewton per square meter in ultimate limit state persistence. This is a slab, this side is free. These are the yield lines, but we do not know what is this angle. So that's why we call this lambda A. Of course, the portion that is there in the middle, it's of course beta A minus 2 times lambda A. The work done by the external forces is then equal, for instance, for this triangle, it's lambda A times A divided by 2 times Q, and the mean deflection is delta over 3. And we got this 1, this is also a triangle, 2, 3, and 4 times. That's where the 4 is coming. The other part is rectangular, so it's beta minus 2 lambda times A multiplied by A, and the mean deflection is delta over 2. The work done by the internal forces is this yield line projected on this axis of rotation. So it gives you A times M and times the angle of rotation, which is delta over lambda A. And we got this 2 times also on this side. Then we have this bending or this yield line projected on this action of rotation. Then we got lambda A as length. So we have M lambda A and then multiplied by the angle of rotation, which is delta over A. And we got this 2 times. E is equal to D. We get M out of it. And this is the expression for M as a function of lambda and beta. So we got this expression from the previous slide. Take care, this is the limit values of lambda and beta. We must maximize the bending moment. It means that the first derivative must be equal to 0. We take the first derivative in function of lambda. This 0 means that this element, which is an easy equation, must be 0. So lambda is then given as a function of beta. For this lambda, the bending moment is maximum. So we substitute this lambda in this formula, and we got the maximum bending moment is Q8 squared over 24 times a factor depending on beta. So we have now optimized the angle here. That's in fact what we have done. Now the question was, when lambda is 1, for which value of beta is that? Lambda is 1 means that this is 45 degrees, and this is the 30, 45, 60 rule. So on this balcony, when can you apply the 30, 60, 45 rule? So lambda is 1, 45 degrees, but lambda is given by this expression as a function of beta. So this can only be 1 when beta is very, very large. So this means that the 30, 45, 60 rule in this case is in fact only valid if there is no influence at all from the other nearby corners, because that means beta is almost infinite. Now let's take the example when A is 1.5 meter and B is 5 meter, then beta is B over A. It's 10 divided by 3. And if you fill in delta in this equation, you find lambda is 0.82, or this means that this angle is more or less 40 degrees instead of 45 degrees. 45 you find with the 30, 45, 60 rule. And the load is 10 kilonewton meter per meter, so the bending moment, it's easy to calculate with this formula, is 7.7 kilonewton meter per meter.